Euler's method is a method that will allow us to calculate approximate slope fields mathematically. If we thought about this point here that I've started with, when x is 0 and y is 1, if we were going to sketch the particular solution on this slope field, we would start at that point and we would follow the slope field, but you could quickly see that we're going to have to start to bend up. And our slope field would then tell us about what this needs to look like. It'd probably look more like this. And so that's just drawing the solution to a particular slope field. But now we're going to look at what would it look like to do what we've done mathematically. What did we do when we drew it? We took the point we started at and we followed that slope exactly, and then we changed based on the other slopes we saw. So when x equals 0 and y equals 1, our first slope, dy dx, would equal 2 times 0 minus 1. So our first slope is negative 1. And so we would travel for some distance at that slope of negative 1. How far would we go? Well, Euler's method will tell us things like use 2 equal steps to approximate f of 1 using this differential equation and the initial condition of f of 0 equals 1. What does it mean to use 2 equal steps? Well, what that means is if we are trying to approximate f of 1, that means we want to know what y is when x equals 1. And if we started at x equals 0, then we're going to do 2 steps. We're going to do the first step where this distance is 0.5, and then we're going to take another step where that same distance is 0.5, so that in total we're doing a total change in x equal to 1, because we had to go from x equals 0 to x equals 1. And so what I encourage all students to do, there's all kinds of like table methods and things, but I think what you really need to do is think about exactly what we're doing. We're going to start at the point 0, 1, and we're going to go with a slope of negative 1. How far are we going to go? Well, we're going to go for x is 0.5. So this change in x, or dx, is 0.5. What we're looking for is what is this change in y, or dy? Because we have an equation for this. We know that dy dx equals slope, which equals 2x minus y. And in our case, for those original x and y values of 0 and 1, this slope is that negative 1 we just calculated. So if my dy dx equals negative 1, and I know that my dx is 0.5, then I can write dy equals dy over 1/2 equals negative 1. Well, if I multiply everything by that 1/2, dy equals negative 1 times 1/2, or negative 1/2. So if I go back to my picture, I know this delta y equals dy is now negative 1/2. And so that means I also know the coordinates of this next point are over 1/2, down 1/2 from 1. So this is now positive 1/2 on the y. That's the new x and y coordinate. And I'm going to use that same slope that I used before, 2x minus y, because that's the slope field. I'm just slightly farther along up here in my picture. So the new x is 1/2, and the new y is 1/2. So 2 times 1/2 is 1, minus 1/2 equals 1/2. So I've actually, let's clean up my picture a little bit. I've started to come up a little bit. My slope started at -1. Well, now I'm a slope of 1/2 about. So this is my slope, dy dx equals 1/2, but it also equals the change in y over the change in x. And we've said that our delta x is going to be 1/2 each time. I've got 2 steps of 1/2. So I'm going to replace this with 1/2. And now solving this equation, I'm really going to multiply both sides by 1/2. And my dy equals 1/4. And so to think about what happens in our picture, I'm now going over another 1/2, but this time I'm coming up that rise, or that dy, of 1/4. And so this is the new point. What is that new point? Well, it's a total of 1 in the x now, and it is 3/4 in the y. Why is it 3/4? Because I was at 1/2, and I added 1/4 on top of that. So what did I really do? I went over 0.5, down 0.5, from a starting point of 0, 1, and then I went over 0.5 more, but back up 1/4. And this intermediate point was 0.5, 0.5. This is truly what's happening in your slope field. You're doing something like this. So our new value is 1, 3/4. And so that means my approximation for f of 1 equals 3/4. So here's another problem, just like you might see on an AP test. Let y equal f of x be the solution to the differential equation dy dx equals x minus y minus 1, with the initial condition f of 1 equals 2. What is the approximation for f of 1.4 if Eulers' method is used starting at x equals 1 with 2 steps of equal size? So those underlined pieces are important. I know, because of f of 1 equals -2, that x equals 1 and y equals -2 is where I'll start. I also know that I'm looking for y when x equals 1.4. And since we're doing 2 steps of equal size, then my delta x will be 0.2. So we're going to start at this point 1, -2, and now we'll find our slope. Our slope will be equal to dy dx, which is equal to x minus y minus 1, or 1 minus a -2 minus 1. Well, this is 1 plus 2 is 3 minus 1 is 2. So what that really means is I'm going to come over 0.2 and up however much it takes to have a slope of 2. So this picture clearly identifies what we have. Our slope, or our dy dx, is equal to 2, because we had 3 minus 1 equals 2. And I know that dy is the thing I'm looking for, or change in y, and change in x, or dx, is 0.2. So now if I multiply this, both sides by 0.2, I have dy equaling 2 times 0.2. I'm going to write 0.2 as 2/10, because I struggle with decimals, I'm better with fractions. 2 over 1 times 2 over 10 is 4/10, or 0.4 if you'd like to use fractions. So now I can erase this question mark. I know this is 0.4. I also know that the new coordinates of this point are 1.2 in the x, and the -2 that I was at plus 0.4. Well, that's going to be -1.6. So that's the new x and y coordinates. Those are the new coordinates that go in this equation here. Plugging in the new x and y, I get a slope of 1.8. So now from this point over here, I'm going to go over another 0.2 in the x and up a dy or delta y that I'm not sure about, but I know that again dy dx will equal 1.8. The dy is the thing that I'm wondering about, and the dx is that 0.2, or I'm going to write that as the fraction 2/10. I'm going to go back to my fractions to be able to finish this out. My change in y, or dy, is 1.8, or 18/10 times 2/10. Well, that's going to be 36 over 100, or 0.36. So that's what I'm going up, 0.36. Well, we're going up 0.36 from -1.6. So we had -1.6, or -1.60, and we're adding to that 0.36. A little bit of math work back from 5th or 6th grade gets us -1.24. That is our estimation of f of 1.4. So we'll finish out with a little bit harder example. dy dx is 2x minus 2y plus 1. And this time we're told that we have a point of 3 comma k, and we're asked to use Eulers' method starting at x equals 3 with a step size of 1. So we're only going to do one step, and it's going to be 1. And we're going to get an approximation when x equals 4, y equals -4. So I'm going to start with a picture. This first value is over 3 up k. And our ending value is over 4 and a y value of -4. And we also know that our horizontal step size is 1. We don't know what our change in y is. And we're going to draw this diagonal. So starting with what I know, dy dx is equal to m, and it is 2 times x minus 2 times y plus 1. Starting at this point, 3 comma k. So that means x is 3. Y I don't know, I'm going to call it k. So my dy dx, or my slope, is 6 plus 1 is 7 minus 2k. Now I don't know my change in y, but as I look at my picture, it's going to be the difference between this y value and this y value. So I could write dy as -4 minus k, because any height is always the upper y minus the lower y. Now I'll set up my equation. Dy dx equals slope equals change in y, or dy, over dx, and I'll replace everything I know. Dx is 1. We just said our dy was negative 4 minus k. And we previously found our dy dx to be 7 minus 2k. Well, this is really just the equation 7 minus 2k equals negative 4 minus k. I could add 2k to both sides. I could add 4 to both sides. K equals 7 plus 4 is 11. That is the solution to this harder problem.